pause that thought, whatever you're on, give me 5 seconds and go to the thermo review so we can go over some of those. This is the one that you have the answers to. So I'm going to dedicate more time to kids down to you right now. So I'm going to try to show my key. It's a little small, but I'll talk through it some. So for number 1, you guys probably noticed number 1, for my problem set. Does anybody have the review right in front of them? Mine is not right in front of me for some reason. What does it say?
Number 1. It says how much heat is absorbed when 92 grams of water at 25 degrees Celsius is converted into steam at 120 degrees Celsius.
Perfect. Okay. I'm choking on gum. It's good. So 25 to 120. You know you're going through one phase change because 25 water's in liquid phase, so I like to draw little graphs. It doesn't matter if I'm going through all the phase changes. I'm going through at least a couple here. So I'm starting at 25, which is liquid. I'm going to 120, which you know is gas, because water will boil at 100 degrees Celsius. So I need to see that there actually are there actually are 3 Qs here to account for. Whenever we used to do chemistry, we used to not account for the different specific heat capacities of ice, steam, and water. So I'm actually going to adjust the sum. So this first little fragment should be Q1. And how do you find Q1 from 25 degrees Celsius to 100 degrees Celsius? So you see there is a temperature change, right? So temperature change is? Okay, so Q equals MCAT. So you should set up with this right here being 75 degrees Celsius. I'm not sure that's the first step. There we go. 75 degrees Celsius. And the M is 92 grams. And the C for liquid water is 4.18 joules per gram degree C. So we know how to do that. The second phase, or the second piece of information given to you is when you have a flat line here. So my little graph has a flat line. And that's delta H what? That, because it's vaporizing from liquid to gas, right? So Q2 includes vaporization. Do you see a temperature change? No. So what equation do you use? Mole times delta H. That, right? And that value I would give to you, but you know it probably by now, it's 40.6, 40.7 kilojoules per mole. But the only thing is just very first step, you would have to take your grams to moles. Third Q is what? We're on the graph here. I hear MCAT, so you're telling me it's from the place where we just ended to the very end. So Q3 is whenever you are changing temperature again, but what's our temperature change here? Right, from 100 to 120, so that's 20 degrees Celsius change. And this C, so MCAT is what you're telling me to do. This C value is like 2.05 because it's the specific heat of gas. Our steam is 2.05 joules per gram degree C. Temperature change here is 20 degrees C. Okay, that's not a negative sign, that's just a dash. So I'm just going to walk through methodology here, and as long as you have your methodology right, we're in good shape. I know I had to go over number 3 and number 5. Okay, so basically if you have 3 different Qs here, once you get done, you need to add them up. Just make sure they're all in joules or all in kilojoules, whichever you like better. All right, number 5 or 3 here. Okay, yeah. Oh, that's all right. I think I can do it from here because I remember some of these. Okay, so number 3 was a question with a metal and water. And a lot of times it'll say the metal is boiled. And I think that's really the only part we're missing what that means. When the metal is boiled, that's its initial temperature. But the metal boiling is it means it's in boiling water. So initial temperature of metal is actually 100 degrees Celsius. The final temperature of the metal was 41. But that's also the final temperature of the water. And the water started off at 25 degrees C. So your temperature change is 16 degrees Celsius for the water and negative 59 Celsius for the metal. Who got those temperature changes? Okay, so those of you who got temperature changes, you probably got the whole shebang right. The thing that was hard to see is that when it says boiling metal or boiling water, it means the metal is also at the same temperature of water. Everything else is standard like we've done before. I think we've done a problem like this a million times now. So this is when you have a calorimetry experiment where you're exchanging heat between metal and water, and you have Q equals Q or MCAT equals MCAT. You divide by the variables you know. You solve for C of metal, blah, 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 blah. Once you plugged in your data from your chart, you should get A high specific heat, I understand, but 7.09. Who got that? 7.09-ish. Okay, beautiful. This one I saw some wrong answers on your paper, so I really want to go over number 4. Whenever you feel something cold, you're holding a test tube or a flask or whatever, and it feels cold. It feels cold to you because what's happening to your hand? Right, energy is being removed from your hand and going where? Into the system, right? Into the test tube, into the chemical reaction, whatever. So if that chemical reaction requires energy from you, that means it's requiring energy as its theme here, which is endothermic. So absorbing energy from this into the system, energy being taken in or heat being taken in, positive enthalpy of reaction or positive Q, however you want to say it. It just means it's endothermic. There's many ways to say the word endothermic. But the scenario of a cold test tube, or why does a test tube feel cold? It's because it's pulling energy from you, and so it's requiring energy. Does that make sense now for my people who had negative? Okay. Number 5, do I have that one up here? If I can barely see it here. I'm just a little bit bigger. Okay. Okay. So this information was given to us on the paper someplace right here. 45.02 kilojoules per mole of ammonia. That information is given to us. It's also in your textbook. If you didn't know I know you didn't, but if you didn't know the heat of fusion, I think this was fusion, of ammonia, you could have Googled it, just like I told you the standard ones for water. There's a standard one for every different compound, because they're just different. They have different melting points and stuff like that. So if I gave you 86.2 grams of ammonia, your job was first to go to moles, which is kind of our first step for a lot of these. And this is kind of like delta H of anything like we had for water. It's just a different number. It's 45.02 kilojoules per mole. So if you had to figure out how many kilojoules that required, it was just multiplying across via stoichiometry. So about 230 kilojoules. We got that one. Okay. Anything else on the unit review? Nay? Okay. On PS 17, I'll go over one of these right now because I feel like PS 17's been with us for a little while here. So let me get myself a page. All right, PS 17. Somebody's gonna have to tell me which one they want me to go over. Shout it out, don't be shy. 7. I like to hide stuff from myself. Okay. 7. How many moles of acetone Oh, there's the energy. I just found it. What's it later? Okay. Sorry, slow slide here today. All right, so 7. How many moles of ammonia? Actually, I put ammonia's on your sheet, right? Ammonia? Yes, okay. Moles of ammonia can be melted by the addition of 200.56 kilojoules of heat, given the fact, and then what's the volume of that gas at STP? So for ammonia, you would, if you looked in your book, you would have seen a whole chart of delta H baths and a whole chart of delta H fusions for different components of the, different compounds. So delta H fusion for ammonia is, anybody? You guys know that one? You may have written it down. 23.4 kilojoules per mole. So if you don't know a value, it's not because you don't know. It's just because you didn't know where to find it. So that value would be a standard given value for you on that problem. So what would you guys start? So those of you who did it, what did you start with? Which of these values did you start with? I'll wait on you guys forever if I got to. 200.56 kilojoules, right? That's the fact, right? So we have to be able to use this and cancel from here. What's next? Right, we're going to divide by H fusion. We're just going to flip the conversion factor so we can cancel. 234 point nothing. Oh, sorry, 23. My bad. 23.4 kilojoules per 1 mole of ammonia. Okay, so check. We've used both of these. What's our question again? Finding moles, and boom, we're there. So kilojoules and kilojoules cancel. So 200.56 divided by 23.4 is 8.57 moles of ammonia. All right, so those of you who figured out the next part of the question is because you just remember a bit more from our last unit. When we have moles of a gas and it says add a CP and it says find the volume, there should be a number that springs into your mind. Everybody? 22.4 what? Liters per mole. So then you're just going to take this 8.57 moles and then times by 22.4 liters per 1 mole, and you'll get the volume that it takes up at that space, or at STP. Yeah.
On this paper, it says 35.
It says what?
35.5. Yeah.
Oh, it's 191.98 liters. Is that the question? Hold on. Where do you see 35? Oh, answers. Oh, I've got this nice little, no. Did I change the value on yours? No, you had ammonia. This is the, I had scratched out the answer. I'm not sure why. I changed the answer for you. But this is the correct value for the heat of fusion of, or no, this is vaporization. No, it says fusion. No, this is fusion. Just go with the, as long as you understand the method, we're in good shape. I just want to point out to you that that H fusion would be given to you in the book, and you would get your moles and then multiply by molar volume to get to your volume. Yeah, is that right?
When I had Googled the heat of fusion, I got 5.65 kilojoules per mole. Is that vaporization that I had seen?
That might be.
35.5.
No, okay. This is vaporization. If I'm looking at my work right, this is that. So if you looked at the the fusion, you got, what did you say again?
I got 35.5 as my final answer.
No, what was the heat of fusion? Yeah.
5.65 kilojoules per mole.
5.65 kilojoules per mole. Okay. Let me start from here. So I accidentally used the vaporization constant number 7. I think it's because it makes sense when you use vaporization, you're making a gas, right? So I made a mistake. I put melted in there. When it doesn't melt to make a gas, it vaporizes to make a gas. So my bad, I put melted, and that probably threw you guys off because you were correlating melted and gas, and that doesn't correlate. So, but the methodology is using a constant, whichever one you used. Sorry, I used the vaporization, or that makes sense. I use the vaporization one, and that's moles of gas, but it actually asks for melting in the problem. And then I went to liters. But as long as you got the process, we're in good shape, guys. I'll fix that for next year, people. Okay. How about 9 and 10? Do we know how to do 9 on the PS17? Okay. Oh, hold on. No, number 3 on PS17. Let me backtrack. Number 3 requires you to talk about a pebble. And the pebble was dropped into, it was hot, and it was dropped into water, and you knew the mass of water, you knew the temperature change of water, and you just naturally already know the sea of water. Was that a calorimetry problem in the traditional sense where you set up the little boxes? No. How did you do it, Gwen? Just right, so you knew that the Q is equal to Q, where the pebble was losing water, losing heat, and the water was gaining energy, but you didn't have enough information for Q equals MCAT for pebble. You knew just the fact that all the information about water. So once you kind of put MCAT in for water here, that will give you Q of water, and if you know Q of water, you actually do know Q of pebble, or how much energy the water gained was was the heat lost by the pebble. So the Q's are equal. You just kind of set up the thought of the law of conservation of energy first, and you use Q equals MCAT to find it. So those of you concerned on that one, that's what you got. And then number 10, we briefly talked about this yesterday. How do you start this one? Do what? Now draw a heat curve. What was the temperature initial? Negative what? Negative 5 degrees C. And what was the temperature final? 1, 2. Sorry, I went too far. What was the temperature final? 175. Okay, so then you would have had gone through solid, liquid, and gaseous phase. Those are increasing in temperature, so what equation is relevant to SL and G? Q equals M cap, and with their appropriate C and their appropriate delta T, because it's dependent upon the phase change transitions here. And then what equation would you use for here and here? Right, Q equals moles times delta H. So I can't go over this one anymore. I think I've gone over this same problem 5 times now. So those of you who need extra help, I'm here for tutoring today. Okay, yeah.
I did the work. I don't know if I messed up or not, but I got like 11.4, and it said the correct answer was 12.
For number 10?
Yeah.
I got about 12 kilojoules.
Like I got like 11.4,
That's probably right. Sometimes I use 4.184 for the specific heat value, and it alters it a little bit. I can check it in a second. Okay, let's do ourselves a favor and jump up. We're going to play Kahoot real fast on thermo to kind of wrap up thermo for now. You can stay with a partner, stay with somebody you want to work with right now, and make a hybrid of your name. Whew.
I guess I don't have time for that. What if we both enter hybrids of our name, Max and
Okay, I'm going to launch this baby.
Max and Max for you, and then if we go through it, we get double points.
Here's the game pin.
You know what? I'm going to start alone, then you start alone. When your line crashes, then I'll just
Hey, I got next to you. Sign Asia by herself. If you would like to work with somebody, you can.
There we go. Nice to you, Max.
Alright, take another couple seconds to join. I'm fixing number 7 because I made a mistake. I can't make mistakes. I should just talk about some numbers.
Follow me add me on Snapchat.
So, anybody else want to join?
San Jose.
Alright, take 10 more seconds and we are starting. I don't think you'll need a calculator. You might need a calculator actually now that I'm thinking about it.
The almighty yellow
Okay, after this we are starting a new unit, okay? So let's get this party started. I'm ready to be done with thermo. Alright, if you don't enjoy that, I will leave the game pin. It's just slow. And we're gonna move on. Alright, start. Are you ready? 11 questions.
Slow.
11. I'm going, if a chemical reaction releases heat, it is A and Woo! Yes, okay. I'm going to slay you people. Red and green. Who is this? Oh, okay, got it. Specific heat of substance is constant. It's a yes or no. Alright, you don't have 19 seconds for this. Make a choice. Okay. So the specific heat of a particular substance in its particular state is constant. That could have been more elaborate, but we mostly got the point. A specific heat of a substance is different than other substances. Keep it up. If an endothermic reaction in a beaker, sorry, that beaker will be blank than the beginning. Hey, we just reviewed this. Literally just reviewed this. Don't be that guy. Okay, yes, I'm going to explain this. Okay. I'll wait on you. Thank you. I know we just reviewed this, but I need to review it again. In an endothermic reaction, the beaker will be blank than the beginning. So the beaker itself is absorbing energy and using it. It's gone now. So what happens to its temperature? It drops. It should go down. Even though I know you're like, oh, it's absorbing energy, but it's using it. So it's totally gone. It's been used and put into bonds. So the bond energy means lower. It's going to be colder. Just basically, you should just remember that if something is endothermic, it gets cold. If something is exothermic, that stuff gets hot because it's putting energy out. Okay? And the beaker is the surrounding, so that's why it feels cold. Heat required to raise 1 gram of Celsius by 1 degree Celsius is called... This is my favorite part. Keep it up. Okay, straight up definition. 5 people. Good try. Heat of fusion is, what's the definition of heat of fusion? It's got to talk about phase change, right? It's got to talk about melting or something. So that one's just gram degree C and heat, joules, gram degree C, that's specific heat capacity. Keep it up, people. During a chemical reaction, heat is absorbed. This reaction is called... I know. Good theme for the day. Okay, I think we're getting the point here. We all should know what endothermic means by the end of today. Water specific heat is 4.18 joules per gram degree C. Mass is 10 degrees. Temperature increases by 10. Calculate the heat. See, let's put them out the calculator. You probably use those out the calculator.
Hope you're right, bud.
I got that right.
It actually, okay. So it's mostly right, but the units are wrong. I meant to change this after because I went back and put it in joules and versus calories. So how did you guys do this math? You can do this math in your head, right?
Times that.
Okay, so 10 times 10 is
100.
100 times 4.18. 418 joules. Then how would you get to calories? 418 joules, how would you get to calories?
Add 2.
You guys remember this? 1 calorie is equal to 4.18 joules. So if you have 418 joules, how do you get the calories? Yeah, you divide by that. So 1 cal is 4.18 joules. So that actually should have been like, what, 10? 100 calories.
I was like, wait a second.
My bad. That should have been 100 calories versus joules. I didn't change the units after I changed the question. But I'll give that one back to you. My bad. I'll give it back to you. Identify correct unit of heat or energy produced or absorbed during a chemical reaction. Just units. Answers on the board. Both places. See? It did say it right there for you. I'm not going over that one. Name the device to calculate heat changes. Device.
Don't screw up, guys.
Whoa! That was awesome! Okay, now I want you to realize heat is heat and temperature is temperature. So if I said calorimeter is to heat, as temperature, as thermometer is to, or Celsius, something like that, yeah, okay.
That's Erlen Meyer's list.
If temperature is increased, blank is also increased. Think about definitions. That's more right. Yeah, kinetic energy. Yeah? Okay. Temperature changes during a phase change. True or false? These are, we got two more.
Every time I saw
We're nine. That was almost one.
Shame on you three people. Shame.
Shame. Four.
You should know temperature changes the flat, there's no temperature change during the flat phase.
I have one question.
One more. In an exothermic reaction, the energy in the chemical bonds of the reactants is... You have to read.
I don't know.
You have
I
to
don't know
read.
Read. Stored energy storage is not the word. Therefore, it's false. Storage is not the word.
Just a couple more seconds. Alright, last person, okay. Okay. I'm going to explain this one to you via a picture, okay?
When you get second and last question.
Alright, be quiet for me. How does this look like on a diagram? The energy of the bonds of the reactants is greater or lesser than the products. Okay, so if it says in an exothermic reaction, draw a curve for me that looks like an exothermic reaction. So does it go here to here, or here to here? It's got to be exothermic. It's got to go releasing energy. It's got to go like this. So it's going to start kind of higher, and it's going to end lower. Because this needs to be reactant energy and product energy. The product's energy is lower because there's a release of energy here. This is delta H and this is negative. So it's releasing that much energy. If the other way, doesn't it look like it's absorbing energy? Yeah? Knowing the or y-axis is potential energy or absorbing energy. So reactant energy and bond, in terms of bonds, are higher than product energy bonds. So that's the answer. The bonds in the reactants is greater than the energy of the product bonds. So it's really to our diagram. It's just in words versus diagram.
You didn't get your joke there.
No,
You said in the lower.
I don't get it.
Way lower.
Got you. Got you. All right. Woo! Shahana. What? All right.
Darn it.
Here are my top people. Oh, nope, not that. There are my top people there. All right, I'll give you some more money shortly. Okay, I'm going to forget.
I can't believe you lost.
Can't believe you did
I
either.
feel like bad.
All right, I need this.
Jake Sullivan.
Okay, so I was going to give you. Go back to your seats for me. Go back to your seats. I have to make a decision based on grades. Like I don't pick a grade unless I like it. You know what I'm saying? Got you? Alright. So last night I did not make you do reading guide 15 because I didn't want to stretch you out because you already had PS and review. So I'm going to talk about reading guide 15 as best as I can today so you can read less and do the questions, okay? So I'm going to do reading guide 15 and like the information, and then I'm also going to go ahead and start chapter 16, and that's just we're going to go ahead and jump right into solutions so that we can do hopefully do our lab tomorrow. If not, we'll do it Thursday, okay? So I want you to write down properties of water. That's the first thing. I'm going to show a video. You're going to write down all the properties of water, okay? So we're doing chapter 15 stuff in like 10 minutes. It's real short. Chapter 15 is about water, and we're pretty familiar with water. We're pretty familiar with the properties. You see it every day, stuff like that. Stop sneezing, Matt.
Sorry.
You really should stop. Okay, here we go. Write down as many properties as you can. Pew pew.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature.
Okay, so I'll leave that there for a second. Here, you should abbreviate though, like high ST surface tension, high C heat capacity. You know what that is now. High C, okay. And then delta, change in density. Yeah, do you guys know? You probably missed a little bit from one of the values we looked up in a book one time, but yeah, water changes in density based on its temperature. So you know how the ocean works. The water at the top is pretty warm. The water at the bottom is pretty cold. The water at the bottom is cold and more dense as well. That's why it stays at the bottom until something kicks it up, like El Nino or La Nina, or you know those earth science terms that I'm just throwing out there. So I don't know, ocean currents. There you go.
Let's take a look at each of these in turn.
Jot down just something about it as we go.
Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions.
I like to call this attack of the water molecules. What is it doing? It's attacking the sodium chloride, but it's not attacking the whole thing. It's attacking bits and pieces, right? So this isn't a lattice, an ionic lattice, which is like that little, just you can see all the pieces together. And those attracted ions can be pulled apart only because water's attraction for chlorine is stronger than sodium's attraction for chlorine. And it's just because there's two water molecules ganging up on one chlorine. And that's going to happen on the sodium as well. There's actually 6. This image only shows 2. There's actually 6, and that's why we can pull the chlorine and the sodium apart from each other, because there's 6 waters against one of those. It's kind of an unfair battle. Water wins.
This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water.
Okay, so what does cohesion mean? Right, so co means, remember, like co or like co-workers, cooperate, things like that means together. So that means water with water. Adhesion to other polar things like what? Not the example in the video. Think of everyday life. Huh? Okay, yeah, it does stick to like xylem and phloem and go up and down the plant, specifically the xylem, because phloem is for food, glucose. Adhesion to like think what do you normally drink water out of, people? Okay, plastic or glass, right? Any kind of material that has some sort of polar nature to it. So I'm going to say H2O plus a cup, and you can think of, glass or plastic there, but it will stick to that. And, that graduated cylinder? You read that, what's that thing called? Like the meniscus. Why is there a meniscus? Because of what property of water? Well, yes, it's polar. That adhesion, right? It's creeping up the sides of the glass. That's why it does that. That's why you have to read the bottom of the meniscus.
Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
I learned about that in college. I didn't know that ice actually gets more dense water actually gets more dense until about 4 degrees Celsius. So it's really, really, really cold water will be at the bottom of the ocean or bottom of the lake. But once it freezes to like zero, between 4 and 0 degrees Celsius, it's going to kind of start to get you freezing. It's going to actually start to float because it's less dense. So the density of water kind of increases in density and then it peaks out and then it's going to drop because the ice formation occurs and there's a big gap in the middle of it, makes it less dense. So didn't learn that till I was like way older than you guys. Thought that was kind of cool. Okay, so water is pretty easy. There's not a whole lot we're going to talk about other than like the practical part of a solution. So we briefly mentioned an IMF that holds water together. What is it? Hydrogen bonding. And is hydrogen bonding really a bond? No, what's a better word for it? Attraction, right. And there's not a whole, some of this is basically review, so I'm flying through this initial part. Let me know if you have a question. So we have a video, that video told us how hydrogen bonding and the polarity of water work together to make all of these properties of water. So to create the high surface tension and the adhesion and cohesion, to create the low vapor pressure. What do you think low vapor pressure refers to? The what? No, not heat capacity. So what do you think vapor refers to? Gas state. What do you think pressure refers to? Pressure meaning like collisions with a container wall, right? So if it's a low vapor pressure, what is water not doing very well? It's not vaporizing, nor is it causing pressure. So that's why water doesn't vaporize like that out of the ocean. We like it to have a low vapor pressure. So I'm going to say the slow vaporization process is kind of what that refers to. We already know what high heat capacity means in high vaporization. It's just a lot of energy used to vaporize it. And so those last two, that one we just talked about and this one, they go really well together. So there's not a lot of new stuff there, but write down what you need to, and then we'll talk a bit more. And then chapter 15 reading, I will be quite busy. Okay, what is the shape of water? The molecular geometry, the shape of water. What do you mean? Bent, right? Why? Okay, but why is it bent? What's pushing the bonds down?
The negative and positive polar.
But what's negative on the top? Not the atom. Okay, let's draw a Lewis structure. The what?
Feels like
Let's draw a Lewis structure. I believe you. Let's draw a Lewis structure. Lone pair, thank you, Lord. All right, so we're still drawing a Lewis structure. H2O. How do I draw a Lewis structure? What do I count? Give it to me. Valence electrons. How many valence electrons does hydrogen have? 1. So there's 2 times 1 valence electrons is 2 hydrogens plus 6 because oxygen's in the 6th group. So, ooh, I know it's hard when I'm in the valence electrons. 8. 8 valence electrons. Okay. How do I? What's my next step in drawing those structures? Okay. You choose your central. Yeah. You find the central, which is oxygen, and then you do
you're licking.
ligands. Look at that vocabulary. 2 hydrogens. How many electrons have we used so far? 4. 2, 4. Okay. Where am I going to put the rest of them? Right, I cannot. H's are special, remember? H's are special, they get the duet rule, meaning they can only accommodate 2 electrons, so are the H's full?
Put the other 2 on the O.
Yeah, octet, oxygen needs octet, so that one needs a lone pair and a lone pair. And I'm supposed to draw it like this to confuse you, okay? On the sheet, you would remember how to look at the ligands and look at the lone pairs and say, oh, 2 ligands, 2 lone pairs, that's going to give us this bent shape. Like this. Because these lone pairs, I'm actually going to draw them both on top. Now, these lone pairs pushed away that bond and that bond, so it gives it that bent appearance. Quick review there. All right. Who remembers most of that? Some of it? Some of us are like, add more electrons. Okay. No, it's good. That's been like a good month and a half ago. Okay. This is new. Okay, this was not in the video. Okay, we have all experienced surfactants before, yes?
Sure.
You mean like, you know what I'm talking about, like soap. We've all experienced that? We know what soap is. Okay. I hope that we've experienced it at least once in our life. Maybe more, if you're lucky. It depends on your belief system, I know. Soap, a fancy word for soap is surfactant, okay? This is the definition, or this is the purpose of a surfactant. I'm going to write down some of this information. Summarize as needed. And that is not one big word. Intermolecular bonds. Intermolecular bonds. Ooh, I put bonds. Oh gosh. I mean like forces. Yeah. So, you know, soap. Okay, we've maybe all washed dishes before, or we've maybe had something really oily in our hands before. If you just put oil and water together, do they mix? No, we know that. We've dealt with that most of our life. Like this lava lamp, oil, this is blue water, it's just distilled water. They don't mix. You can see that they just separate again. This is therapy. Okay. So they don't mix. They just kind of glob together and they stick with what they stick with, right? So if I wanted to make them mix, even if I shook them really hard, this would always separate back because they just don't mix. They're polar and non-polar. So I can actually force them to mix by adding a surfactant. And a surfactant is like soap. It's also a detergent. So examples would be soap and detergent. I think I have a group working on Mythbusters with detergents. This will be a good little addition for them, okay? So detergents get the oil and stains and stuff like that out of your clothes, right? Well, that's just washing in water, and you might have like a greasy spot from cookout on your shirt. How does it get out of the shirt? You add a detergent. So what happens is, I'm going to show you from this image, actually. We cut the lights for me, Neely. This image is kind of hard to see. The oil droplet is nonpolar. Nonpolar things do not mix with polar things unless you make an attachment, okay? So this big thing here, I can barely see it here, this big thing here is kind of the soap molecule. The soap molecule has this hydrocarbon, this big wiggly line is like C, 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 C with H's all around it. You'll notice that's just a big blob of carbons, which is nonpolar. So this nonpolar part interacts really well with oil. This part over here, this sulfate, has an ion charge. And ionic charges interact, because they're like the most polar of everything, they interact really well with water. So if you have like this perfect hybrid with a nonpolar side and a polar side, it actually attaches to water and to oil, and it brings them together and it washes them down the drain together. So it kind of forces the interaction that normally wouldn't occur. So that's what a surfactant does. So that's how you get clean. That's how your clothes get clean. And there's usually like some fragrances and stuff like that that are added to make you smell good too. Okay, so that's how chemistry saves you from smelling horrible. I mean, it can't save you all, but the smart board is having real problems today. And like this week and this year. It's just not this year. Okay, so that's it for chapter 15. Here's my jokes for you. Sorry, we just can't be together. It's because I'm fat. No, it's water and oil. Thank you. Okay. Hey, sorry. Thought a joke would just break the tension. Splat on the ground. Help! I'm dissolving! But theirs are insoluble. Because he's a polar bear. Since for you, you're not polar. Ah. And then James Bond. Hydrogen bonds. Ha. Okay. Thank you, Ms. Inlow. Get up, get yourself stretched right in. We got a little bit more, okay? Go see somebody about something useful. Like go bond with somebody or like talk about the soap you use. If you use soap. Talk about the bed structure. That is not nice, dude. If your name is on the board, please come and see me right now. Because I'm gonna forget. You know I will. Natalie, you want to know? Sorry, I got 6 plates. Jay, okay. Hold on. Look, like, hold up. The smart board is acting up. Okay, for you and Jay, Tag, Gwen,
Tug, Hayden, Talia.
Here, pass it out to your group. Hannah. Okay, Ian, come back to me now. Come back to me. We are starting in 5, 4, 3, 2, 1. Okay, you have 1 minute to draw me a cartoon. You know how solute and solvent interact now. I want the picture to indicate what a solution is, a solute is, and a solvent is. I want to see what you know.
I can't draw.
It's okay. I can't worry. I can be able to
I was never able to draw.
Hey, you're wasting time. You got like 45 seconds now. This was on the warm-up. If you got a warm-up sheet in front of you, maybe that's helpful. Little names on there. Kool-Aid, excuse me, Kool-Aid. It can be a cartoon or it can be a real nice picture. I mean, you're drawing it. This is a little morbid.
Okay.
That is so pretty.
Solvent with water. Oh no. Hasty cold. What? That's the guy.
Oh,
Is the solvent size?
Where's his
Where's
body?
Where's his spine?
He just his spine's gone.
Those are his legs, though.
His spine just got raised.
Where's his torso? Those are his
Okay, I don't know what the solvent is, but it did some damage. Okay, so we should realize solution is the total, yes? Your picture should indicate a total solution of solvent and solute together in some way or form. Always remember the solute is the smaller amount, and this is the body, right? So the smaller amount is the solute, and then the solvent is the larger amount. And I'm going to call this hydrofluoric acid. Because hydrofluoric acid dissolves bodies.
What?
Good to know!
You just need to bury a body, right?
Yeah. Okay. And then I have a joke. Like, I just love hanging out with you, chlorine. He hates sodium. No, is that, I don't know, is that water? What, where? I'll never forget you. It was a sad love story. Getting dissolved can be traumatized.
Water always brings.
Okay. So, the next thing, I know you guys gotta stay with me here. The next thing I need you to indicate someplace on your picture, or it can be another picture, is there are 3 steps to dissolving. It's not an easy process, okay? The first thing is step 1. Solute gets expanded. So you have like sodium chloride or something that's all together, it's just going to expand. There's energy that it takes to do that. It doesn't just happen. It's going to take energy to expand. Does step 1 make sense?
Sure.
Okay. Step 2 is the solvent, usually water. It also has to expand. Well, what do you think water has to really overcome that's holding it together? Hydrogen bonds, right. So when I say expands the solvent, that probably means to break. I'm going to say break really loosely. Break the IMFs, aka the hydrogen bonds. Do you think both of these take energy? Am I doing something to the solvent and to the solute?
Yes.
Yeah, I'm like breaking them apart. It's probably going to take energy. So is that an endothermic process or an exothermic process? Endo, because it's taking energy in. So this process here has got a positive delta H. This process here is a positive delta H. Okay, those are just the first 2 steps. And then they become this happy like family, and they come together and they start to interact with solutes and solvents multiple times. And that usually, most of the time, is a happy place. So they release all their pent-up energy. So what do you think? Endo or exo? Say again? Exo, because they're probably going to release energy, and that's going to be a negative delta H. So that's how a solution forms. I know you didn't know, but now you know. You're informed. It's a process. So basically, solute breaks apart, solvent breaks apart, then they come together. They mix. All that's happening inside of things when they're dissolving. All right, I'm going to go past this in a second. I know some of you guys are drawing images, but the process is more important. Who's ever seen I'm going to get rid of my evidence. Who's ever seen a curve called a solubility curve like this? Where it's like amount dissolved and like temperature. Some of us?
I did just now.
Oh, good, okay. I'm glad I can help that. Okay, we're going to talk about that soon, okay? So, do we remember this phrase?
Yeah.
What does it mean? Solar and polar. I was hoping you'd forgotten. Did you forget? Yes, you did.
Yeah. What is that?
Was about to dissolve. We saw you.
Great, now we're gonna get sued by ACDs.
I know.
The salt is up in water in a beaker today. The ions work apart in the usual way. The molecules of water get the ions apart. A salt solution formed, but that's only the start. Homogeneous, same throughout. Homogeneous, same throughout. Solids that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and a polar solutions just won't mix, but a non-polar solvent like an E can fix. Like dissolves light, fuller and fuller. Like dissolves light, fuller and fuller. And all the solvent molecules used up better stuck to the solute. I need your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation.
Okay, this is the part I want you to write down. This is the part I want you to write down. I want to rewind it. There's going to be vocabulary. And go ahead and draw this graph. Go ahead and draw it. So, you'll see, I can't see the bottom very well, but just put like I did, amount dissolved on the side. It actually does have a unit of grams of solute per 100 grams of water. We'll add that at the end. And over temperature. So temperature is on the x-axis. Amount dissolved is on the y-axis. And draw yourself just a little curve, like a little exponential growth. And then we're going to label the 3 words: saturated, unsaturated, and supersaturated. You'll see it in the video, and we're going to kind of just briefly talk about it again. So I'm going to scooch this back just a tad. This is easy, I tell you. This graph, you'll get an example of it in just a second. It's pretty easy to read. Oh, and if you want to title it, it's called solubility curve, because it's curve and it's talking about solubility. We're not creative, this chemist. It's amount dissolved on the y and temperature on the x. Okay, I'm gonna scooch this back just a tad.
I need your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation
On the line.
Saturation on the line. Distill some water molecules unstuck, then we're safe in dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility.
Okay, so saturation's on the line. So guess what? If you're down here, you're under the line. Do you think you're undersaturated or supersaturated? Under, because you're under the saturation line. Yeah.
Unsaturated, put more in. Unsaturated, put more in. If you put more solute in, then you be dissolved. Better supersaturation situations involved. The excess falls out as a precipitate, or the solution is unstable, so you acetate. Supersaturation, precipitate. Supersaturation, precipitate. A salt is on the water in a beaker today. The ions broke apart in the usual way. You need it all.
All right, the last part we haven't learned yet. Okay, so let's review kind of the terminology. Terminology. I'm going to go back, and I'll come back to these notes in just a second. Let's talk here first. All right, so if you need some clarification on what do these terms mean, saturation, there's a specific, Kendall, you with me? Okay, there's a specific way to write it, or to think about it. It's like you've maxed out your amount of solute that should be able to go into that amount of solution. So it's always temperature specific, so it does have a little bit more of a definition to it. But if you add more, that means it is past capacity. So I'm going to say saturated means at capacity. And that's kind of as basic as I can define saturation. So a solution is going to have solute in it, and it's that if you add just one more little crystal of solute, it would cause precipitation. It would cause the whole thing to solidify. And I'll show you that tomorrow because my solutions were not ready today. So how do you think I would define unsaturated in the same fashion? Not at capacity. So that means that there's more that you could add if you wanted to. More solute you could add at that particular temperature. Without any consequences. You just keep adding until you meet saturation. And then how do you think I would define supersaturated? Past capacity or above capacity. So that means you've got too much solute. Now, how would you even get there? Like, how would you put too much solute without it precipitating out? Most of the time, you have to heat up the solution to make it supersaturated, SS supersaturated. You have to heat it up and then slowly let it cool down so you don't disturb it. Because if you disturb it, it would drop out of solution like you saw. So in that same video, so that saw that white stuff kind of fall into the solution. It's because the solution is really unstable, so it tends to like just totally solidify whenever you have a small disturbance. All right, thumbs up when you got these terms. You'll see these again in your reading. So let's look at this graph together. Pass back a handful, and then your extra thing. So this is yours, right on it. It's all yours. If there's not enough, let me know. Here, I'm gonna touch that. I'm gonna hold them for Annabella. Kendall, is there one more extra coming back there? Tadeja, pass one over. Alright, you guys see the graph on there, right? The graph, not the crossword puzzle. I know you're tempted. Okay. So on this graph, you'll notice it's a different line for every single compound. So we've got, name that. Hurry, name it.
What's sodium?
Nitrate, good.
Ammonium
Chloride, and then
potassium
chlorate. Good. Okay, so you know some of these weren't terms, and I'm not going to spell them out for you all the time. But this graph is what we just saw in the video. But individual lines represent the solubility of independent or individual salts. So let's look at some of the questions here. On your graph, do you see there's a couple of extra lines? This one has it, but it's not dashed. So looking at the questions next to your graph, for which salts is solubility least affected by temperature change? So which salts is solubility least affected by temperature change? Anything that's kind of has a zero slope, right? Which has the most zero of slopes? So sodium chloride, if you need a colorful pen or something, try to use just something different colors, you'll be able to see it better. So here's mine right here. So anything that's pretty zero in slope. So sodium chloride in this case would be our one that's least affected by temperature change. Approximately the same amount will dissolve from 0 degrees Celsius to 100 degrees Celsius. It doesn't really change. Okay, for the next one. For most salts, what's the relationship between temperature and solubility? So this is question 1. So tell me what you mean by that. Right. Increasing temperature increases the solubility. And how do you know that? What do you see here, Caroline? Right. So we have a positive slope going on here. So a positive slope shows us that, I'm going to highlight a couple of them, like ammonium chloride is going up in solubility with increasing temperatures. Potassium nitrate's increasing in solubility with increasing temperatures. Sodium nitrate's increasing, and you can see that trend across the board. What do you notice that's different? What's one that does not follow that trend? Which one's going down? What's that name, NH3? Ammonia. Good, I don't know who said it. So ammonia is going down, and then there's also, on your graph, there's another one. Do you see the other one on yours? What is it? Name SO2 for me. Sulfur dioxide. Okay. So that one's going down. So what's the general rule for, and you'll notice those are gases, okay? So ammonia is a gas, sulfur dioxide is a gas. So what's the general rule for gases? So is it a direct or indirect? Indirect, and you should see a what slope? Negative slope. Okay, so negative slope would be increasing temperature causes a decrease in solubility. Why? Why do gases decrease their solubility when they get heated up? Go for Max.
It's like the particles start bouncing around and move. So like.
Say again, particles what? They spread out, and what happens to them?
I guess that's not supposed to be the particles.
Okay, so gases, gas particles, I'm going to say gas molecules speed up, and that's because we know that temperature is correlated to average kinetic energy, and so they speed up. Then what do you think they do when they meet the surface of the water? they just pop out, right? They're zooming around. They evaporate very quickly out of the solution. So the gas molecules speed up, and I'm going to say leaves the solution easily. And that's kind of an explanation for that. Solid particles, they're kind of hanging out inside the solution. They're attracted to water a lot. Gas molecules, generally, they're nonpolar. Generally, not all the time. So they don't attract with water well. So they don't have an attraction to water. So that's another reason they leave solution very easily. I have a group that's, I think, in this class, maybe another class that's dealing with that too. Yeah, I think it's another class actually. Okay, so we have, I'm actually going to stop on the gases for a second. On your guys' questions below, tell me what a couple of these are. We're going to go through maybe 2, and then I'll let you guys work on that. And I'll think about going further, but I might be killing you today. So we all know what the line represents. It was in the video. What was on the line? Saturation. Okay, so I want you to write down the line represents saturation or a saturated solution. So you got that on the top of your paper, okay? Or wherever that is on your paper. So let's do like maybe the first 2 together, and I'll let you guys work on the rest for a minute. According to your graph, because I'm going to look on your graph. Is potassium bromide on your graph? No, I did this to myself. Okay, I'm looking at my graph then. Potassium bromide is here. Looking at that graph, how many grams of potassium bromide will dissolve in 100 milliliters of water, which is just what our axis is referring to. 100 grams of water is 100 milliliters of water at 80 degrees Celsius. So all you do to read this graph is to look at the 80 degrees Celsius, which is right here, and you draw, you follow, trace your finger up until you pass over potassium bromide, and then that's where it crosses the saturation line. So then you go over to the y-axis and you say, oh, it's at 100 degrees or 100 grams. So it's just really learning how to read the graph. So at 80 degrees Celsius, potassium bromide, it's a little bit less. It's probably like 99, but it's right at 100. So 99 grams of KBr would dissolve there. Yeah. Because it's on the line. That's the saturation point. So you guys do according to your graph, because you have sodium nitrate on your graph. And we already, oh no, we didn't discuss those things. So for the potassium bromide one, use my graph, but for the potassium, or for the sodium nitrate one, use y'all's graph. What'd you guys get for 2? Any takers? So I'm going to use my graph here. Is it this one? Okay, so at 10 degrees Celsius, it's about 80, right? But that's 80 in how many milliliters of water? Right, that's only in 100 grams or 100 milliliters of water. So you got 80 and 100 milliliters of water. How much would be in 500 milliliters of water? Yeah, so you're timesing by 5, so 400. So you're going to be 80 grams per 100 milliliters of water. So basically, I'm just going to times by 500 milliliters of water. And that this is just doing dimensional analysis, but it's just times by 5. And so you get 400 grams. That would dissolve. Keep going. Actually, let's scroll down so you can see the graph there. The KBR is in the red up there. Would you guys get for which salt is most soluble on your graph at 40 degrees Celsius? Sodium nitrate. And actually, I know you can't see that graph, but can you see Ki up there at the top? Can you assume it probably crosses and is probably higher than sodium nitrate on your graph? It most likely is. So on your graph here, Ki is here, but it probably extends or extrapolates further. So at 40 degrees Celsius, Ki would be the most soluble. Okay? And then I'm going to skip down to the one with 80 grams of sodium nitrate, and you guys have that graph in front of you. When 80 grams of sodium nitrate are dissolved in 100 grams of water at 10 degrees C, what type of solution is formed? So we have three options here. Saturated solution, unsaturated solution, and supersaturated solution. So remind me 80 and 10. Here we go. So looking at your graph, sodium nitrate, at 10 degrees Celsius, there's a marker here, there it is. At 10 degrees Celsius is here. Draw the line up until you meet with sodium nitrate. How many grams are at the saturation point of sodium nitrate there? An approximate. How much? 75, 78, something like that. So that right there is about 78-ish grams per 100. If I put 80 in, what kind of solution is that? Supersaturated, because it's above the saturation point. So if I put 80 in, that would be a supersaturated solution. If I put 60 in, that would be a unsaturated solution because it's under the line. So if 80 is above the line and 60 is below the line, those are two different types of solutions. Does that make sense on how you're reading the graph? Some of us are like not responding. Okay. Look at the KBR one, then on the next the graph I have, 100 grams of KBR at 60 degrees Celsius. So KBR is this red one here at 60 degrees Celsius. I'm going to go in green. 60 degrees Celsius, look up at the line. What's the saturation point? Maybe like 85, 90. Okay, 85 or 90. If I put 100 grams in, what kind of solution do I have? Supersaturated. Okay, go ahead and stop that. Look at the molarity worksheet. You guys work in pairs for the next 15 minutes on the molarity worksheet. It's okay.
True.
Thank you for bearing with me. A little long today, but you guys have 15 minutes. Please work on that molarity worksheet so we don't have to do it tomorrow. Work on part 2. Yes, I'm going to take one first. If you cannot see the images very well, here's model 2 right here. No, I'm getting ready to staple them. Hold on.